Okay, so now we are on to the topic two, which is noise control and room acoustic. So uh, as our course learning outcome, you have our CLO 1 and 4 and the core reading material as followed here. So based on this video, so you can go and have a look at it again if you're interested. It's actually not in your slide. So I just put it in because the video has a very good representation of how we perceive sound, our working mechanism inside our human body. What is it that makes us perceive sound and how sound is generated. So sound is actually just a vibration in the air in sound wave. So there's a difference in wavelength, frequency, and all this combined makes a sound. So they cannot travel in a vacuum, but they can only travel in solid, liquid, and gases. So the sound that we experience in our daily life is all traveling through the gases, which is the air around us. So the way we perceive sound is through the variation in the pressure of the air, which will have an effect on our ear. And from our ear, it will send a signal to our brain, and that is how we perceive sound. So they have a few factors behind how a behind the sound wave that we have perceived. So the first is the wavelength. So this wavelength is the distance between any two repeating point on a wave. So if there's a if there's a repeating wave, then it's actually called a resonance, which we will cover later on. But generally, when it comes to wavelength, when it comes to our perceive of how we perceive sound, we actually do not want to have any repeating wavelength. So we only want to have one wavelength of that particular point of the sound, and that will be it. But this is one of the factors from the sound. So besides that, we actually have frequency, which is also one of the factors based on sound. So depending on how high or how low the vibration is or the number of cycle based on the sound wave, then if you have a very high frequency, meaning vibration, in within 1 second, so we will hear a very, very high pitch. So this is actually represented by a unit which is hertz. So at a low vibration, meaning there is not so much vibration per second, then it will be at a lower frequency. And at a higher frequency, then you have a higher number of cycle. So here the example here will the explanation here will provide a more detail of what I just mentioned. Okay, so next we have our pitch, which is the frequency of the sound as perceived by our human hearing. Meaning if it's a low pitch, we will hear it as a low frequency, and then at a high pitch note, that is caused by a high frequency sound wave. So the level of frequency range that we can perceive is from 20 to 20,000 hertz. So next off is the amplitude, meaning how much energy is coming from the sound wave. So basically, sound wave is just movement in the air. So the more or the higher amount of energy in it, then the greater the sound and the more intense the sound we are able to perceive. So that is what it means by amplitude. And then next we have our quality of sound. So some sound can be pleasant and some can be noisy. So usually a very pleasant sounding sound have a regular pattern. Okay, so for noise, they actually have a very irregular pattern. So there's no repeating pattern. So when we perceive this sort of irregular sound, then we call it as a noise. Okay, so in sound, we have velocity of sound, which is fast the how fast or velocity is the distance moved per second in a fixed direction, meaning how fast the sound is moving. So we have here, which is a unit for wavelength. We call it lambda. And then we have your velocity, which is in meter per second. And then we have your frequency. So depending on the type of material sound is moving through, either if it's an air, water, or gas, the three state or solid, they will have different velocity. So here, this table is it shows you the typical velocity when sound is moving through this material. So you'll notice that when sound is moving through this material at air, they will have about this level of velocity. But as the medium which the sound is moving through this material gets more solid, then the velocity increases. So here, velocity of sound is independent of the rate at which the sound vibration occurs. So which means that the frequency of a sound does not affect its speed. So how fast a sound moves is actually independent of how high or how low the frequency is actually different. There's actually no impact behind it. So it's actually also unaffected by variation in atmospheric pressure, such as those caused by the weather. So how fast a sound moves is actually independent of a lot of variable. Okay, so just an example of how a wavelength formula can be used in the question. So this is a very simple example. You have a wavelength with 440 hertz, and then you have a velocity of 340 meter per second based on this sound wave. So we can actually calculate out what is the wavelength of this sound using the formula given. So we have your V equals to F multiplied by your lambda. You have your information given. So by just dividing the velocity over the frequency, you'll get that this wavelength, sound wave, is actually repeating itself at 0.77 meter, meaning there's 2 points at which you will hear a repeating sound. So some object can have a higher wavelength, some object can have a sound wave can have a lower wavelength. It just depends on our room acoustic, which we will cover later on. So this is to show that any particular sound, they have a variety of factors behind it, ranging from their frequency, how loud it is, their amplitude, the frequency, the pitch, and then finally their wavelength. So when it comes towards building services in a room, we want to actually try to eliminate all these sound wavelength, meaning you do not want to have any repeating wavelength. So this is in regards to how good the environment is in a room, so that when you are playing, let's say, a music, or you're speaking in a room, or you're watching a video, then the sound is pleasant to you. There's no repeating sound and it's clear. So this when we are designing a building, we will actually have to take into account. So when it comes to normal houses, residential houses, I don't think there will be much of a problem to get a very good acoustic. But then there will come a case where it comes to a particular room. Usually, when you go to a condo, you notice that if you were to go to a lobby or the lift lobby, sometimes it's not designed. Sometimes it's not well designed. So, in a sense that when you go into a lift lobby, if you were to try to talk there, you'll hear resonance or echoes from being in the room. So this is where the room acoustic fails. So because steps has not been taken to ensure that there's no repeating of sound and to ensure that there's good sound environment, meaning the room is too rigid. So any voice that's produced inside that room, they are actually repeating off it, off the wall. So this comes back to what we have, which is the resonance. So although we cannot see it, your daily objects, from small to big, they actually each have their own frequency at which they vibrate at. So when objects starts to resonate, meaning the vibration, they are coinciding and they are vibrating at the same frequency, then this is the result of what we call a resonant. Meaning instead of just the object bouncing off the sound wave, they actually increase in vibration. So when this object starts to resonate, then there's some very bad consequences behind this sort. So building and even bridges can resonate. So let's just show you a very quick example of how what will happen when resonate happen in a building. So this is a bridge in Japan, and it shows a resonant vibration. So this is due to the wind blowing through the bridge, and then there's also vehicles which all add up to how this bridge starts to resonate and move. So you notice that the bridge starts to turn wavy. So this is very dangerous in terms of if in terms of there's actually a lot of movement on the bridge. So when we build a building, it's not designed to move so much. So when you move too much, then there will be a collapse for the building or even the bridge. So this is a case for bridges. There's actually cases for building swaying also, but this is also due to this is not due to just wind lah. So when it comes to a building resonating, it will mostly come from earthquake. So in Malaysia, we are lucky that we don't have so much earthquake.
Like your deliciously satisfying new omelet sandwich. Try today.
Okay, so you notice that this thing is moving. So actually, the person filming it is actually standing from the opposite side of the building. So it's not the video moving, but is the building moving. So you can see here it's more clear that the building is swaying since you can see the base of the building. Okay, so just a few examples, a visual example to show that every object, as we are building more and more or bigger building or higher building, then these are the problem that we start to encounter. So usually when this happens, then we have to find out is it a very critical failure or not. So just a few examples for you guys to have a very graphical look at it. That when it comes to designing a building, this sort of thing we will have to take into account. So even in Malaysia, when it comes to designing high rise or even bridges, uh, when it comes to designing high rise, even though we do not have earthquake, there's actually a fixed design rule that have to be followed. So although in Malaysia we don't have earthquake, when it comes to designing high rise, we also have to implement the steps taken as though the building is gonna face earthquake. So just additional information for you guys to know about. Okay, so next we have your measurement of sound level, which we measured it in terms of watts. So it's a power, it's a rate at which sound energy is produced at the source. So its unit is in watts. And then next we have your sound intensity, meaning the sound power distributed over a unit area, which is watt over meter square. So you are given a formula which is I equals to P over 4 pi r squared. And then next you're given a sound pressure formula, which is I equals to P squared over rho V. So sound pressure is the average variation in atmospheric pressure caused by the sound. So their unit is in Pascal. So there's always a relationship between intensity and pressure due to how sound is being generated. So we know that sound is actually just a movement of particles in the air or in any state of material. So it's just a transfer of energy from movement in the air to our ear, and then our brain perceives the signal, and that is how we are able to perceive sound. So this movement on the air is how all these formulas are generated. So we have this intensity, and then we have sound pressure. So sound pressure, the formula is based on the relationship of sound intensity. So don't worry about all this formula. It will be given to you. You don't have to memorize it. Okay, so next it comes to two types of threshold for us human being. So the first being threshold of hearing, and then next we have our threshold of pain. So the only difference behind these two is that for threshold of hearing is how weak or how weak a human can perceive or detect a sound. So at 1000 hertz, so it has a value of for sound intensity, we can hear up to this level value. And then for pressure, up to this level value. And then when it comes to threshold of pain, is how loud the sound we can perceive. So if you go any further, then it will actually damage the ear mechanism, as you've seen in the video lah, which is in which our human body, we have a very delicate system of hearing. So if you hear a sound that is too loud, then it will actually overwork that particular organ. And then when that organ is not able to work, our brain is not able to perceive the signal, then we will not be able to hear the sound. So this is the value lah, which is for intensity about 100 watts per meter square, and then for pressure it's about 200 Pascal. Okay, so when it comes to measuring sound level, we do not use intensity or pressure. So we use decibel, which is represented by dB. So this is actually a logarithm ratio of two quantities, which is represented by this. So your given n, which is a value or a number in decibel, and then the formula here is actually based on intensity and pressure. So this and this is the same thing. So depending on what you are able to get or what you're given in a question, if you're given the I intensity, then you make use of the formula of this part. If you're given pressure, then you make use of this part of the formula. So this and this is interrelatable lah. They both come hand in hand. So our human ear is actually a very amazing thing lah. Meaning we can hear a very, very quiet sound and we can hear a very, very loud sound. But we are not very good at detecting how loud or how quiet the sound is. So when it comes to logarithm, it's just a method of simplifying values. So logarithm values can be very, very big and very, very small, and is able to make it into a very it is able to make this value into a very simplified value. Okay, so next we have your another formula, which is the sound intensity level. So we have to make use of this logarithm to work out what is the sound intensity level. So we have what is the intensity of the sound being measured divided by the intensity of the threshold of hearing. So this sound intensity level, the formula, is based off of our threshold of hearing. So the formula is made to measure how loud the sound is in relationship to our hearing. And then next we will have our sound pressure level. So this is also the same, but this is in terms of our threshold of hearing. Okay, so example of how this formula can be used. So you're given a sound pressure of 4.5 times 10 to the power of negative 2 Pascal, and then you are measuring it under certain condition. So you have to calculate what is the sound pressure level, given that your threshold of hearing is 20 times 10 to the power of negative 6 Pascal. So this is a very simple example of how we can work out what is the sound pressure level. So we just put in the given value here into the formula, and we are actually able to get, for this example, the sound pressure level is at 67 decibel. Okay, so another example is just a sound. It's also under sound measurement. So we have to calculate the changes in sound level when the intensity of a sound is double. So here, instead of giving a value, this is to show that when we are doubling the sound level, then what's the changes towards the sound level when we double the intensity of the sound. So here you are not given any formula or any value. So you have to assume it as unknown. So you will still be making use of the formula for sound intensity, but instead of just putting in value, you have to assume the differences between sound level 1 and sound level 2, which is the initial and then the final. So if we put it in here, so hopefully you still remember your maths. So by rule of logarithm, we can actually combine this and this together if you want to minus it. So we can get it into here, meaning by rule of logarithm, this one minus this one, we can put it into an equation like this, which is divided. And then you will simplify it, we get something like this, which is 10 log 2i over I. So the I is still intensity lah. We only have one level of intensity. So based on this, you can actually remove away the unknown, which is the I. And then we will get 10 log 2. And when we compute this equation, we get that when we double the energy, it actually gives an increase in 3 decibel. So this is just a way of showing that when we double the intensity of a sound, the actual sound level that increases is just 3 decibel. So hopefully you remember I just put in a slide here on how what is the 7 rules of logarithm, just for reference purpose. Okay, so this logarithm, as mentioned, is just a way to measure a very, very big range of values, meaning from a value of 1 to a value of 10 billions. So it gives a simple way of measuring of lots of zero, being able to simplify lots of zero into a very more simplified value lah. That's what logarithm is all about. So for sound, you have to make use of this logarithm in our measurement of sound. Okay, so next off, we have combination of sound level. So we have different intensity. When we want to add intensity, we can just add it like this. And when it comes to pressure, we can add it like this. Okay, so this table shows you how the difference between sound level changes. When it comes to changes between 1 to 3 decibel, as mentioned before, our ear can actually detect a very wide range of sound. But when it comes to different minute changes, it's actually not so sensitive on our hearing. So if it's just a change level of 1 to 2 decibel, the effect on our hearing is not very noticeable. But as it goes higher in value or lower in value, then that's where we'll be able to hear the difference. So this just shows that when it comes to our hearing ability, we are able to hear a wide range of sound. But when it comes to sensitivity, we are not very sensitive to how loud or how soft it is. We are just able to assume that this sound is quite loud or this sound is quite soft. So any changes in sound level, we are not, our ear is not good enough to notice the difference. Okay, so we have your example 4. Okay, so I think this will be your final example. Okay, example 4, you have your combination of sound level. So we have to calculate two sound level, two combination of sound level, 95 decibel and 90 decibel. And then we have to measure it in terms of our hearing intensity, which is this value. So you still have to make use of our sound intensity level formula, which is this. We know that for the first sound is at 95 decibel, and then you're not given any of this value. So we just work it out. Oh, you're given this value. So we work it out. We know that for this 95 decibel, the intensity level is this value when you solve it out. Repeating the same for the 90 decibel, you work out that the value is this. So you follow through all this, and then you work out this is the value for your intensity for your 90 decibel. And then you can just add them together when it comes to intensity, and you'll get this value, the final value, I3. So when it comes to combining your intensity, your sound intensity level, you have to do it in this way, which means you have to work out what is their intensity, the I for 95 decibel, and then you have to work out what is the intensity for the 90 decibel, work them out, and you get I1 and I2. And then from there, you can add the intensity or the sound together, and you get I3. And then from there, you have to put it back into the formula, and you have to work backwards to get what is the sound level for this combined, for this question, for this sound. So when these two is sound intensity is combined together, you'll be able to get the sound level in decibel back. So here, it's important for you to try. So when it comes to calculating logarithm, hopefully you still remember, your calculator, if you do not have the anti-log function, you can just simply use x to the power of y lah, when it comes to function. So for example, if you have an anti-log of y, you can just do 10 to the power of x equals to y. So this is just showing you how to work out the anti-log lah, which you can see here. So here when you move your logarithm from left to right, you actually become an anti-log. So what you can do with this anti-log is just, if you don't have this function, put a 10 to the power of 9.5. Then you'll be able to solve this question. So when this is a bit confusing lah if you don't understand. Okay, so let's stop here.